So yeah, quiz tomorrow. Here's the quiz topics to prepare for, as always, are based on last week's P6. An antiderivative. And differential equation. So those two topics are the two questions: some kind of differential equation, some kind of antiderivative, and yeah, and that's it. And remember, for the differential equation, just show the process. Even if you mess up the integral, messing up the integral is only like a small reduction. It's to separate the variables, integrate both sides, find C, solve for Y. Even if you mess up the integral, you can still show a lot of those steps accurately. You get a lot of points. Here, that's your last quiz.
When you're doing the recap of the last lesson, can you go over quadrature too? Like when you're talking about
quadrature? Just a quick side note. The Greeks were big with turning shapes into squares. So it's just that. In fact, there's this phrase I have heard. It's not really a common phrase, but squaring the circle means to try something that's like impossible or really hard to do. Because the Greeks tried for centuries to turn a circle into a square and they couldn't do it. And then people kept trying for centuries afterwards to do it. Actually, a really fast side note, in the it's like 1870s, 1880s, Iowa, randomly, the state voted to let pi equal 3.2.
What's Iowa?
And it was either Iowa or Ohio. I think it was Iowa. It was one of those like vowel states. But the reason why they did this was because a member of their states found a way to square the circle if pi equals 3.2. Because it turns out, it was proven like 10 years later, that you can't turn a circle into a square using only a compass and a straight edge because of pi. Because pi's irrationality prohibits making this circle into a nice clean square. But that wasn't proven until like the 1880s. And so this guy from Iowa was like, if you just let pi be 3.2, then you can do this. And so Iowa's great idea was to like patent his method and sell it to other states. Like, you can now use our method to square the circle. So this would be a nice little fundraiser. And one of their state senators was bragging about it to a professor at, I think, Purdue, one of those schools out there. The professor was like, you can't do that. You can't just say pi is 3.2. So it all got overridden. But yeah, I forget why I started to say that. But the Greeks like to turn areas into squares. Okay, now to a more relevant recap. So the fundamental theorem of calculus, the FTC for short, just to recap what we did yesterday, let f be continuous. It also works for non-continuous functions, but the proof that we would do is only valid for continuous functions. It's because the proof needs the mean value theorem, and the mean value theorem needs continuity. There's two parts to it. Part one, part two. One is that we have a function that is an accumulation function, which just means that as x grows, you accumulate more and more area underneath this curve. Then f prime is just f of x. We started to explain this at the end of class on Monday. We'll do more examples today to explain it. But basically what this says is that if you were to do out this integral, you would do the antiderivative and plug in your bounds. And then if you were to differentiate it, it just goes right back to where you started from, only you plug your bounds in between. The big impact is that integration and differentiation are inverse operations, because the derivative and the integral, they cancel each other out and they give you just the function inside. And in part two, gives us a nice way to compute a definite integral. G is any antiderivative of f. And why this is confusing and not at all intuitive is that the antiderivative tells you what function has this for its slope, right? Because the derivative is slope. And so if you want to find the area between f and the x-axis from a to b, you just find what function has f for its slope. It seems a weird connection between slope and area.
Yeah, I'm not following that too. So what's the g of b minus g by d?
More space here.
d prime of x equals f.
Yeah, g is an antiderivative of f. I guess I'll write right here. Where g is any antiderivative of f. Again, to find the area, just do the opposite of slope. And we mentioned briefly why it's kind of intuitive how area and slope are opposites, because area is a product of x times y base times height. Derivative is a quotient of y over x, changing the y over changing x. So you've got the most basic levels. The derivative is a quotient, the integral is a product. It makes sense that they're doing opposite things, but still not easy to figure out. Okay, let's do a couple examples for both these parts. First, we'll do one with part 2, the integral from 0 to 2 to the absolute value of x squared minus 1. So absolute value is a piecewise function. And for piecewise functions, you have to break up the integral into all of its pieces. So if we sketch this out, you can see exactly what we need to do here. So to sketch x squared minus 1 absolute value, it helps just to kind of sketch x squared minus 1 without the absolute value. That's just x squared minus 1. All the absolute value does is make negative values positive. So when the function's positive, it's the exact same curve. When the function's negative, the absolute value just flips it over. And so this is the absolute value of x squared minus 1, just x squared minus 1 normally, but anything that's negative gets flipped. And so we want the area beneath this curve and the x-axis from 0 to 2. We want that space right there. So to do it, we need 2 integrals. We need 2 integrals because something happens right there. We pretty much go from one piece of a piecewise function to a different piece. So we'll have 2 integrals, one from 0 to 1, one from 1 to 2. One for each piece of our piecewise function, because again, absolute value is a piecewise function. The part that is the same as x squared minus 1 has no change. So from 1 to 2 is just x squared minus 1, because that function is positive there, so the absolute value doesn't do anything to the function, just keeps it the same. But from 0 to 1, we flipped over our original function. And when you do that, when you change the sign from negative to positive, all you're doing is taking the opposite of it. X squared minus 1 is negative on this integral, and so the opposite of that gives you a positive value. So that's all absolute value does. If the input is negative, it switches the sign. If the input is positive, then nothing happens. And then you just do out those 2 integrals individually and take their sum. Before we continue, any questions there with absolute value? And it's true with all piecewise functions. Okay, we'll just do like the first couple of steps out and we'll let this one ride. So do that's negative x squared plus 1, so it integrates that. Integrates. Should have parentheses. I always forget my parentheses. And then just plug everything in. There's a bunch of fractions, and eventually it gives you some number. We won't finish it off, though. I think you had some practice doing it yesterday. Question, Hector?
I think it's 2.
2?
I think it's
The number 2. That's a surprisingly nice answer. Okay, so those are definite integrals, which again, we would have to have used limits and rectangles and summation formulas. This method is so much better. So only do the method with Riemann sums if I tell you explicitly use Riemann sums to do it. Like the first PSEC question is the only one. Let's do sum with part one. So let's some function, I'll just call it p of x for some reason. Let it be the integral from 3 to x of roots 1 plus t squared. We want to find p prime. So p of x is some function. Oops, I went too far over. P of x is some function that tells you how much area there is beneath this curve from 3 until the x value. We want to find the derivative of the function. So what part one tells us is simply put the derivative and the integral cancel out. And all that happens is prime is just this function f, but x is plugged into it. And that's all. It's an easy thing to do, but it's a hard thing to understand. Why it's so simple is that if you were to do out this antiderivative, you would do the antiderivative, plug in x and plug in 3. And then to find p prime, you would differentiate. So you end right back where you started from. It's just in this in-between place, you plug these numbers in. So now the x is in there. And the 3 went away. Why did the 3 go away? Because the derivative of constant is 0. So that's what goes on there. Now, this function, we couldn't have done this because we don't know how to integrate this yet. We can't integrate that function, so we couldn't have done it this other way. We had to use the shortcut like that. Let's do some harder examples. It is a trig sub, yeah, with tangent. You have to use tangent to integrate that.
Which one's side?
If it was 1 minus x squared. Yeah. Okay. Fair enough. There we go. Let's find big F prime. Where big F of x equals integral from x to x squared. T squared cosine t. So similar to the last one, we could do the antiderivative, plug our bounds in, and then differentiate. But we haven't learned how to do this one either yet. This one is integration by parts. But we haven't learned how to do it, and even if we did, it'd be like by far the slowest method. Instead, it's kind of like think our way through it. If we were to do the antiderivative, also called the antiderivative big G, it would be like big G of x squared minus big G of x. It's just the antiderivative at the top bound minus that at the bottom bound. And then when you do the derivative, it brings you right back to here. Only 2 things have happened. 1, we've plugged in x squared and x. And then 2, since we're differentiating where we have an inside function, chain rule.
Wait, G is the derivative, or G is the inside function, right?
Yeah, G is the antiderivative of whatever this is. Whenever you see capital letters, they almost always mean antiderivatives. Okay, so all we have here is we plug x squared into this, so it's x squared squared, cosine x squared. But then we do times 2x. Because x squared is an inside function, so we have the chain rule. We have a composite function. When you differentiate, when there's an inside function, the chain rule applies, multiplied by the derivative of the inside. And then minus the lower bound, you plug it in, x squared cosine x. And you could combine the 2x and the x to the fourth to make 2x to the fifth. But the main idea is when you have a bottom and a top function, they're both part of your answer because they're functions and not constants. And any function needs the chain rule. F's. We're doing like 3 more examples. So
G is antiderivative of the inside function, right?
yeah, so G is like the unknown antiderivative. Because when you do a definite integral, you find the antiderivative and do the top bound minus the bottom bound.
But then at the bottom there, just plugged in the values of the inside function to the inside function.
Yep.
Plug in the bounds to the inside.
Yeah, because the derivative of the integral function, they cancel out. But after you plug your bounds in. Let's do another one. I think actually like half the piece set is questions similar to this when I make you use part 1. Because I find it to be the most confusing thing. This thing's not that confusing, but part 1's confusing. Let's say f of x now to small f, do the integral from 0 to x over 3 of sine t squared, which we can't integrate. So even if we had all the techniques that are known to do integration, we still can't integrate that function. Part A is f increasing or decreasing when x is root 12 pi? Increasing or decreasing? Well, pi is all under the radical. That's part A.
Why? In this case, why is okay?
Is there a question?
I was going to ask why it's like lowercase f.
Yes, because it could be anything. Customarily, you use uppercase letters when your function is an integral function, but you don't have to. It could be anything. So anything could be used. Again, customarily it's uppercase, but it could be anything. So to see if it's increasing or decreasing, what do we need? The derivative. Yep, just find f prime and then plug your point in. If f prime is positive, then your function's increasing on the interval. If it's negative, it's decreasing. So you find f prime. Try it on your own first, and I'll put up the answer. Do the first step at f prime. So the derivative of this integral function. The rule is just that the derivative and the integral cancel each other out, not until you plug this into your variable. So it's sine of x over 3 all squared. And then since we have an inside function, multiply by the derivative of the inside function times 1/3. So 1/3 sine of x squared over 9. Again, why that's true is that if we were to do the antiderivative, you would do the antiderivative, plug your bounds in, and then differentiate right back to where you started from. You just plugged your bounds in. So I have x for 3 in there. Yes, Chris?
Wait, why didn't you bring down, so you're squaring the terms inside the, I thought it was like sine squared x.
Oh, no, that's just this is sine of t squared. Sine of t squared is not sine squared t. Sine squared t is if it was sine t in parentheses all squared.
Wait, where did you get the times 1/3 from?
So when you plug x over 3 like into your antiderivative, we now have an inside function. And when you differentiate with an inside function, chain rule.
So you plug in first and then differentiate
Basically, yeah.
with how to do it.
That's not right. The short way of thinking of it is just the derivative and the integral will cancel each other out, but not until you've plugged this in. So you plug it in, and this is an inside function multiplied by the derivative. It's a hard thing to understand. Remember, this is the theorem that took Newton and Leibniz to figure out.
So like
Should be easy.
if that was an indefinite integral, you wouldn't have to plug in anything. It would just be the inside function. Like the derivative of the indefinite integral is the inside function.
Right, they just cancel out, yeah.
This works because when you plug in 0 into like the antiderivative, it's just like a constant. So
Yep, exactly correct. Yeah, when you do the antiderivative and plug in the top minus plug in the bottom's a constant, so it just differentiates to 0. The top of inside function, so it gives you chain rule. And then the last step is plug in root 12 pi. Root 12 pi squared is 12 pi. And I made sure it was a number that's on the unit circle so that you would know the answer. Sine 4 pi over 3, all we care about is positive or negative. So which one is it, positive or negative? Yep, because it's quadrant 3, right? Because it's more than 1 pi, so it's down beneath. So our function is decreasing on this interval. So f is decreasing on the interval containing this point. Part B could be as a concave up or concave down on an interval containing that point. So for concavity, what do we need? Second derivative. So we take our first derivative, just differentiate it again, plug in root 12 pi. There's no FTC involved in this one. It's just for concavity, you need the first derivative, so we differentiate again. Also change rule. So sine differentiates cosine, so 1/3 cosine x over 9, and then times the derivative of the inside function. And then plug your point into that. And all you care about is the sign. Is it positive or is it negative? And it comes down to the same thing as last time, just the cosine of 4 pi over 3, which is negative because it's to the left, right? Cosine's the x value, we're moving left since it's over there in quadrant 3. So we are negatives, we have a concave down portion of our curve. So we'll move on from there. So tomorrow in workshop, a good chunk of it will be practicing these kind of questions. I think they're the hardest parts of the week's P set. We're moving on to area now. We actually should be, or I should say, you should actually be able to finish all of the P set after today's lecture. And then we're moving on to like volume stuff on Friday. But the P set just goes up to our next topic, which is area. Other questions before we move on to area between curves? So really from now until the end of the term, we're just doing geometry. We're using calculus to solve advanced questions in geometry. We'll do area for sure, we'll do volume for sure. We might have time to do surface area, arc length, and other topics that actually aren't part of any of the AP curriculums, but they are part of 1801. So first, let's F and G be continuous. Be continuous on the intervals A to B. Such that F is greater than G for all values in the interval. We need continuity because this theorem, again, it's only guaranteed if F is continuous. It also works for non-continuous functions, but not all of them. You have to be some clever syntax. So most of our rules, we need continuous functions that we can use this theorem right here. The area between F and G over the interval A to B is the integral from A to B of F minus G dx.
You can separate that too, right?
If you make it into two integrals if you wanted to, since they have the same bound, the same variable. And this is super informally the integral of the top function minus the bottom function. Because F is greater than G, so F is always above G. So why that's true sketch out two curves. So let's say here's f of x. Here's g of x. Go from like A to B. So we want to find the area between those two curves. So there's no formula for that shape. And so, as is so often done in calculus, to find something hard, the area of the shape with no area formula. We approximate it with something easy. And what shape should we use? Rectangles. Almost any shape would work. As long as the shape is an approximation, you could probably work out a way to find a way to turn it into the exact area. But rectangles are by far the easiest.
Is that really true? It's like yesterday, not saying it aloud.
That was for like three-dimensional shapes, so I don't.
Octagon.
So again, octagons? Ooh, that'd be hard. The problem is you'd have to find a way to define it so that it fills all the empty spots as the number goes to infinity. But if there was a way to do it, I don't see why it wouldn't work. It'd just be,
That's not.
I don't know how you would define it though.
Wait. Is that
But as long as there's a way to like make it work, which is kind of
just
possible.
about my knowledge, actually.
Now,
I feel like you can if you want to.
If you really wanted to, there's be a lot.
I'm gonna do it.
I'm gonna look into it because I can't think of a way to make it work. But it might be able to work. But yeah, so we'll use rectangles, which will work. And then the area is approximately the sum from 1 to n of all of their areas. We know the base of each one is going to be delta x because we're moving along the x-axis for each base, or we're like moving along the same direction as the x-axis. It's just how far you move over each time. The height is just this length right here. And it's like if you had a ruler and you want to find the length of some curve, it's just the top number minus the bottom number. It's just the top function minus the bottom function. F of x of I minus g of x of I. So F minus G is just the height of all those rectangles.
Remind me again, what was the star for? Like we have to I star.
So x of x sub I is the right side of the rectangle.
Oh,
X of I sub star just means any point. Right, left, middle, just means anything.
cool.
Is this a Riemann sum?
Yeah.
It is a Riemann sum. We have that delta x there.
Well, yeah, you can take the limit of that. That's into an integral, right?
Yep, which means we can take the limit and it turns right into an integral. If it wasn't a Riemann sum, if there wasn't a delta x, we'd have to introduce it somehow. But we have a Riemann sum here, so it's all good. Yeah, Chris.
So mathematically, what's different from what we were doing last week versus this week with like x of I star and
So really the only difference is that x sub I is the right side of each rectangle. X sub I star we define to be anything. It could have been the left point, it could have been the right point, it could have been the midpoint, it could have been some random point. It's just x sub I star was more general. So all that says is that you don't have to use the right endpoint. You could use any point for your height.
so it changes nothing about it.
Oh no, because once you go to infinity, all those give the exact same answer.
Okay.
If you only had like 5 rectangles, they would give different approximations. But as n goes to infinity, they all converge to the same solution.
Thank you.
So yeah, so since we have a Riemann sum where delta x is constant, the exact area right to the definite integral, which we have over there. If there's more than one set of, or I should say, if there's more than 2 intersections for your curve, you might need more integrals. Those are always the most annoying questions. No, never. I never get tired of it. And it's one of those small things that like bothers me in students' work when they don't write down limits. I just write it down.
For me, it's the infinity sign. I always have to write like 2 little circles because I can't get the sign right.
it does take some time to like get used to these like mathematical things.
It's so awesome.
It's like in discrete math, you do a lot of brackets. And students have like the worst time with those brackets at first. Some of the brackets are like so ugly. It's like, it takes practice. But no, I love writing down with it. Yes, oh yes. If there are multiple intersections, sometimes your graphs will cross each other, giving you a bunch of spaces where to find the area. A, B, that's C.
Would you just find the intersection points and like add them up?
Yeah, so for this one that I drew over here, there were no intersection points. So the area between the curves, we had to be given start here, finish there, because there weren't any natural boundaries for our region. If the graphs intersect, then you have boundaries. So this question might not have said, find the area between F and G in this range. It could have just said, find the area between F and G, because F and G have intersections, and so there is a natural boundary region. So you don't have to be given bounds. And if you're not given bounds, the graphs have to cross. If they cross multiple times, you have to use multiple integrals. There is no way to make it shorter. It seems like there should be a shortcut to it, but there is no way. Every new pair of intersection points gives you a new integral, because you always have to have the top function first and the bottom function second. And so from A to B for this graph, I have F on top, B on the bottom. But then once it flips, we have to change our integral. Because otherwise you would have negative values, and area is always a positive quantity. We don't want anything negative here. So there's G on top and F on bottom. And again, it looks like there must be a way to combine those into one integral, but there is not.
That's a plot.
It's got to do it all the way out. I don't think you see this on the piece at all, but it's possible. So just got to find your intersection points and be where you need always the top as your first function. If your function's in terms of y, it's the same idea. So here we have f of y and g of y over c to d. In terms of x, a and b are the go-to bounds, a to b. In terms of y, it's c to d, c up to d. It's like here's c, here's d. And functions of x go left to right, functions of y just go up. So here's x equals f of y. And there's x equals g of y. It looks weirder, but all the math is the exact same. You can still integrate, only instead of going left to right with the rectangles, you just stack them up bottom to top. So we want this area right here. But again, the technique is the same. You would approximate it with rectangles. Only again, as I said, you don't stack them left to right. Now it's like bottom to top. So from C to D, you stack a bunch of rectangles. As the number of rectangles goes to infinity, it'll still converge to the exact area. The main difference is the base of each rectangle. If like this was like the base length, what can I call that value? It's not delta x anymore, delta y. Because now each of those is a little jump up. So it's a change in y.
So the other thing is like change in x. X minus change.
It's over here.
Change in x.
Yep, it's going like you're going left to right, so it's like a change in x every time. Because horizontal is an x movement, so it's change in x, change in x, change in x. Now we're going up, so it's changing y, changing y, changing y. Since we have delta y, that will become dy, which means y is our variable of integration. So it's f of y minus g of y dy. It really is the exact same process. It's just the variable changes. You have to kind of switch your way of thinking. In terms of x, top is the bigger number, bottom is the bigger number. In terms of y, the right side has the bigger numbers, the left side has the smaller numbers. And so it's the integral of the right minus the left. That's how the axes are set up, where the more right you go, the bigger you are, the more left you go, the smaller you are. Let's do one example. Let's find the area between x equals 2y and x equals 8 minus y squared. Okay, so here there are no bounds given to us. If there are no bounds given to us, those two curves have to cross. And those crossing points form your boundaries. So the first step is to find the intersection points. We're going to be in terms of y for this integral. So we have two functions of y. So we figure out at what y values does 2y equals 8 minus y squared. I'll give you a second to solve that any way you choose. So again, we aren't given boundaries. We have to find them. These two graphs must cross. So we set it equal to each other and solve it however you want.
We can like check which is greater in like the different intervals.
Yep, that's gonna be our next step. Once we know the bounds, we're gonna figure out which one's right, which one's left.
2 and -4.
Yep, 2 and -4 is what I got too. You could factor, I should just guess and just see if it works. But factoring is probably the smarter way of doing it. So now we know that our integral goes from -4 to 2. If we had 3 intersection points, we would need more integrals. Because 2, we just have a start and a finish, one integral. If we had 3, we would have to break it up to multiple integrals. But we don't have that, thankfully.
Ooh.
So now we know our bounds. But we need to have the right side minus the left side, because area has to be positive, so we need the bigger minus the smaller. So now we need to know which one is the right, which one is the bottom, or the left. Yeah.
So find the intersection points.
Yep.
Move the y squared over, right? And then like calculate out a y.
No, so you could move the y squared to this side and make it positive. subtract the 8. When you solve quadratics, you have to have all your terms on the same side. And then you would factor y plus 4, y minus 2. So when you find which one is right, which one is left, what you're trying to figure out is which one gives you bigger numbers. And so you just plug in any number in the region. So plug any number in the interval -4 to 2. Don't plug in those numbers, guess where they equal each other. And just see which one is bigger. See which graph is bigger. Say ratio, that's actually a word. What's an easy number to use for this?
0.
0 is the easiest number.
0.
Plug in 0 to the first, it gives 0. Plug in 0 to the second, 8, which means 8 minus y squared is on the right side of this interval because it gives you bigger numbers. If you plugged in any other number, it would work.
Greater numbers?
Greater numbers, thank you. Plugged in 1, plugged in -3, they'd all work, but 0 is the easiest. And so the integral is, show in space, -4 to 2 of the right function, 8 minus y squared minus the left function. And then just integrate. See what this gives. I'm not going to finish it off. I forget the answer. But then you just integrate normally. And if you did this and it gave you a negative answer, it means you messed up somewhere because area has to be positive. You could also graph out these curves. It's harder for students to graph these at first because they're not used to y being the variable. But a graphing program like Desmos could help you. Just graph them in Desmos and just verify, do I have my right and left side correct? You can also go to Wolfram Alpha if you want to check any answers and like literally just type in what's the area between this and this, and it will tell you the integral and the answer. So there's good ways to check your work as you do these kind of questions. Yes.
If you wanted to graph it in terms of x, would you just like flip it once you?
Oh, you mean would you just like make them into x and flip them? You could, but you don't want to think that way. It's almost like you want to get used to being able to think in terms of both variables.
Oh, no.
So like y squared is just this. That is y squared's graph. It's just x squared, but going in terms of y.
Yeah.
So 8 minus that means you move right by 8 and you flip it around. So that's 8 minus y squared. And then 2y is just a line, so it's going to be like that. Yes. Oh, no. The quiz is from last week's PSET. So the quiz is, did I erase that already? Yep, just antiderivative and a differential equation. Okay, so a quick break. At 11:33, we'll come back. Continue with some volumes. We're going into volume now. On to 3 dimensions.
What do you mean you go under? What? That's so much information. No one.
Do all 9 cents.
Yeah.
I don't want all the time my limits and my
You're just trying to like not.
No, I mean, you're right for that, but it's the way you phrase it.
Like, I mean, you want to simplify that, you know?
I see what you did. You want like to be like, actually someone present. It's just like, you're right for that, but it's what?
Yeah, you sucker. I don't.
Yeah.
I don't. I mean, I won't judge.
You're judging.
I'm not judging. I'm just surprised. You know, I want to express it too. Makes me feel I just stare. Terrible quality.
Okay, you haven't taken a test. That means go there.
you guys are
And
coffee
is like.
I was literally laughing. No, I was literally laughing. I was laughing because Gabriel kept looking at me.
No way that you named that worse.
And I texted Matt during the class, I should start coughing right now and see what people say.
No, that'd be funny if you send like a picture of like us with like positive tests and see you guys on negative. That'd be. Does anyone want? So do you just like just chill in the room with them?
No key, no key.
I just wear a mask.
Like I'm just like curious like what the dynamics is like.
High chairs are busted.
It's okay, talk out of my angle. I think they will be gone.
They want you gone.
It's okay, it's okay, it's not so much.
Here, why?
I don't know.
I gave you a high chair. So thinking about, oh,
Wait, why do they want you gone? Do you want to stay?
Bro, I don't know, bro. It's just a topic of garbage.
They don't want to give you flavors.
That's toxic.
I recommend kiwi. Kiwi is like very good.
like.
Okay, so we'll continue now. Okay, so now we have covered all that's on the P sets. P sets just that definite integrals and the fundamental theorem of calculus and then some area stuff. The hardest question by far, I think, is this last question, the area question. But it's not hard because of calculus. It's hard because of algebra. You have to figure out a way to express those lines, equations. It's so often the case, the algebra is the hardest part. So now we're on to stuff that's not on the P sets. We're going on to the third dimension, volume. So there's a bunch of different techniques to find volume. We'll learn like 4 of them. But first, we will find volume of solids with known cross sections. Okay, so first, a few words about cross sections. What a cross section is it's the shape you get when you slice a solid in some direction. For example, let's look at a cylinder, but we'll do so in 2 different ways. So I have 2 cylinders side by side. The first one will take a horizontal cross section. If I took this cylinder and I sliced it horizontally, what shape is a cross section? Circle. You can think of a cylinder as just being an infinite number of infinitely thin circular solids all stacked up, like a CD tower. Take a bunch of CDs, stack them all up, it gives you a cylinder. And actually, the volume of a cylinder is pretty much based on that. It's just a circle, but times h. It's just a circle from like 0 to h. So horizontally, we have circles. Each one is the exact same size. Add them all up, you get the volume. If I slice it vertically, right down, going in a vertical way, what shape is that cross section? Yeah, rectangle, or it could be a square. A rectangle more general. Now, unlike the horizontal one where it was each the exact same circle, these ones will change as you go from left to right. As you go from the left to the right, the height is always the same, but that base length of the rectangle will go from very small to its biggest in the exact center and then back to small. But still is just a sum of an infinite number of like super thin rectangles. So think of them all as being like super thin rectangular solids. You can use that to approximate the volume. Now for cylinders, we don't have to do that because we have the volume formula for it. So we don't need to do anything crazy in this case. But if we didn't have that formula, we could approximate the volume with something easier. Rectangular solids, and then just take the limit as their number goes to infinity. It's kind of like if you want to find the volume of a book by doing the volume of each individual page and just taking the sum. That's what this is like. You take the volume of each individual cross section and just add them up as their number goes to infinity. So that's the idea. Let's derive the formula. So this example is really just to show how the formula works. So we'll draw our x and y axes. And we're going to draw a solid with trapezoidal cross sections. So first I'll draw a trapezoid up here. It's a bad trapezoid, it's a bad start to my solid. It's coming out of the board. So like this line you can think is like it's on the board, and then like this trapezoid is like coming out of the board. So it's like coming out a bit. You can picture that. And we have like, I don't know, some cool shape. There's the base of it. It's not too bad actually, as far as trapezoidal cross sections go. So you can think of it as the back of it is flat and it's coming out. We have a three-dimensional object, it's coming out of our XY axis. So just this part's on the axes. The rest of it's popping out. And our goal is to figure out how can I use the cross sections to find the overall volume. So the idea we kind of mentioned, you break the shape into a bunch of solids based on your cross section. So here we'll have trapezoidal solids. I'm going to try to draw an example of one. That's pretty good. So it kind of looks like this. We just break our region into a bunch of those. We do that because we know the volume of that. the volume of the ith trapezoidal solid, we can find the volume of any solid where the bases are congruent is just the area of the base, so the area of the trapezoid, times the height of the solid. What is the height of this solid as I drew it? Perfect, delta y. We know it's delta y because we're stacking them up. So each new one's height is a change in y. Because as I drew this solid, it's going up the y-axis. The area of the trapezoid is also a function of y. It's a function of y because as you go up the y-axis, it changes. They're smaller up there, they're bigger down there. They change along the y-axis, which means they are also functions of y. So the volume of this solid is just the area of the trapezoid times the depth times how tall it is. And so an approximation of the exact volume of my object is just the sum from 1 to n of all those solids. Or again, we're in terms of y, because as I drew this picture, we're going up the y-axis with our solids. Is it Riemann sum?
Yes.
It is, because the delta y is there, which is good news. Eventually, there won't be Riemann sum, but for right now, this is a Riemann sum. And so we just go right to the integral. The exact volume is the limit as the number of these solids approaches infinity. Because as they approach infinity, they get infinitely thin, and they fill the solid exactly. It really is like finding the volume of a book by going page by page. So the volume equals the integral from, or in terms of y, so we'll call it like c to d. Of just the area of the cross-section shape times how tall it is, how like thick it is. That is if your cross sections are perpendicular to the y-axis. So if they're coming out of the y-axis, then their depth, their height is a change in y, and their area is a function of y. If they're going perpendicular to the x-axis, then it's in terms of x. Perpendicular to x-axis. Old school sign for perpendicular. So again, it's just the area of the shape times the depth of the shape dy, and add them all up. As their number goes to infinity, that's what the integral does. Okay. Let's do some examples. These are hard shapes to draw, usually. It's going to be hard to visualize these. We'll do our best. How much time we got? Oh, we got 10 minutes left. It's enough for probably one full example. So let's say we have three minus x squared in quadrant 1. And this is region R. So how these questions tend to work for the introduction questions to the topic is that you're given a graph. The region on the graph is the base of a solid. So R is the base of a solid. And the cross sections will come out of the board. And so we'll find the volume of a few different shapes with different cross sections, but all of the same base. So find the volume if cross sections are we'll do a couple examples of it. So R is the base of the solid. Find the volumes. The cross sections are squares for part A that are perpendicular to the y-axis.
It's the same thing as right.
Yep. So squares perpendicular to the y-axis. And cross-section volume questions, this is like the intro question. You're given a graph, it's the base, it tells you the shape, it tells you which axis you're perpendicular to. The hardest questions, I'll just give you a solid. I'll just be like, here's a pyramid, find the volume. And it's up to you to figure out how to make your x, y axes, which way to take your cross sections, horizontal or vertical, how do you define everything. So that's like the hard example of the question. We'll do those on Friday. So for this one, we're going perpendicular to the y-axis, so we're in terms of y. It's going to be integral from c to d of area of the squares in terms of y. C and D are your bounds for y. So it's where you start and where you stop stacking up these squares that will make your solid. So what is the bottom bound going to be? What's the top one going to be? Actually, it's just 3.
Oh, why?
Yeah, so since we're in terms of y, our bounds are in terms of y, we start from 0, we finish at 3, stacking up our squares. So it'll be 0 to 3. The area in terms of y is usually where the work comes into play. So how I do it is I start with the shape. We have a square. The area of the square is the base length squared. And we figure out how do you put the base of the square in terms of y. So I just like to draw what I call a representative example. That is one base of a cross section, right? And the square like comes out of the board. Oof, I could press undo on that. It's horrible.
Oh, terrible.
Ah, now it's beautiful. But we have squares coming out of the board at us. So this is the base of one such square. And the question is, how can I write that base in terms of y? It's similar to area. In terms of x, the height was top minus bottom. In terms of y, the height was the right side minus the left side. Same thing. The length of this base of this square that comes out of the board is just the right side minus the left side. The right side is the function, but we need that in terms of y. So you would just rewrite the function to be a function of y. It's going to be root 3 minus y. What's the left side of my curve? So that's the right side is root 3 minus y. What's the left side of the region?
0.
Just 0. Because that's x equals 0. X equals root 3 minus y. So it's just root 3 minus y. So the area of the square is the base length squared. The base length is this line, just the right side minus the left side.
It's a B is just like I would say that you have to change in that, so like the distance between the x values.
Yes.
And that is
Yep. It is an x value because all of our functions are functions of y. So x is the output. So it is like an x length. And so the area in terms of y is just root 3 minus y squared, or just 3 minus y. So to find the area If our cross sections are squares going perpendicular to the y-axis, we just draw an example of a base of one such square. The length of that base is the right side minus the left side. And the area of the square is the base length squared. And then you would do the integral and plug in your bounds. Let's see whatever that happens to be. So it'd be like 4.5, 9/2. 9/2, 4.5. Trying to picture this shape is a challenge. It's kind of like you know, like the cornucopia horns. It's kind of like that, but more square. Although if you were to graph this thing out and like make it perfectly, it would be like curved lines. Like you would like notice the squares were there. I can try to draw it. Like if you were to draw this, it's almost like here is the base of it. And here is the opening. And this kind of curves right down to there. So this is the shape. And if you picked any like random point in there, the cross section at that point would be a square. And it dropped vertically, but it's supposed to be a square. Like that's the opening. Yes, Chris.
I'm confused. Isn't it 9 minus 9/2?
Yeah.
Oh.
Yep, and 9 minus 9/2 is 9/2.
Oh, okay.
Let's just try to set up one more. And then we'll break and then continue on Friday. Let's do rectangles perpendicular to the x-axis. Whose height is twice the base length. Yeah, its height is twice the base. I'll re-sketch my region effects. So now in terms of x. So now everything's in terms of x. So instead of 0 to 3, we go 0 to what number? √3. Because now in terms of x, we go from the start to the finish. We're going to line up rectangles whose height is twice the base, all the way from here to there. So the volume is integral from 0 to √3. Most of the work is trying to find the area in terms of x. How do we find the area of each of the rectangles in terms of x? So this is my representative example of a base length. That's the base of the rectangle, perpendicular to the x-axis, and it comes out of the board. Twice that length, so going like here maybe. And I do it in a similar way.
We have the base, we have that one, right?
No, so this is the base of the rectangle, and so the height is like 2 times that. So the area in terms of x of rectangles is base times height. But there's no x's yet. The height is 3 times the base. So it's b times, 2 times the base. B times 2b, so 2b squared. The base length is right here, for example. It's the top minus the bottom. So it's just the curve minus 0. So it's 3 minus x squared. But it's 2 times this length squared gives the area of each one. And then you'd have to multiply the whole thing out. We're not going to do that. Equals a number. So we're out of time, so we'll continue this on Friday. It is on the P set. A lot of times for questions like this on like an exam, I just say write the integral that gives the volume. So that like this is your answer. Because they often don't turn into very nice integrals to compute. So. Okay, so we're good to go there. So again, the P set should be good to go in terms of all that you need to tackle that. I recommend trying to get that done early because the last question is definitely challenging. Okay. So Kaylee, we're all good to go here.
Thank you.
Just gonna stop recording.